Science is based on the study of the forces. It's the bedrock that supports our technological breakthroughs, which are themselves based on well-tested theory. But these theories, which make up the standard model, are still very much partial theories. All interactions in our known world, our physical universe, are governed by the forces, but we don't yet fully understand how they work, and even less so do we know the properties of particles. We only know their gross features of charge, mass, and spin, and even that has had to be deduced or inferred. It's all a question of scale, and the truth is that the scale of the particle is that small that it simply cannot be determined empirically. The four known forces are the electromagnetic force, the strong and weak nuclear force, and gravity. Starting with the electromagnetic force. Broadly, the standard model has assumed that a changing electric field will always induce a magnetic field. In the same way, a changing magnetic field also induces an electric field. The assumption is that one cannot have the one without the other. But two magnets can and do interact without inducing an electric field. It may be there, hidden within the body of the material itself, but it's neither evident nor measurable. Therefore, it may be that the magnetic field is more fundamental. It may therefore be a primary force. The question is, what is this magnetic force? Does it have a material structure? Even though we're unable to see it, we do know that there's always some correspondence between the structure of what we can see and between the material forming that structure. In other words, the whole is the sum of its parts. An iron ingot, for example, will always comprise iron atoms, and in the same way a piece of wood will always comprise carbon atoms. It's a dependable correspondence principle. Perhaps in the same way, a magnetic field would simply comprise the material of very small magnets, or particles, made up of a north and south pole, exactly as do our permanent magnets. If so, then they would be magnetic dipoles that would amass in the form of strings with their north and south poles attached. However, we also know that symmetry is an essential feature of all particle physics. Quantum physics explains everything, but only in generalities. Essentially, there's a requirement for a profound underlying orderliness that somehow exceeds locality constraints. So, we're looking for a perfect symmetry, and to advance this, then one would also need each end of those open-ended strings to attach to each other to form a circle. And if many such strings were amassed, then the result would be that the attractive charge of each part of those strings would be countered by the repelling force of the neighbouring strings. And we propose that it is this attraction and repulsion that generates the spin of the entire structure. Essentially, all those strings would move against each other in a structured clockwise or counterclockwise direction. We've now pointed to the possibility that our magnetic fields are actually structured from strings of dipoles, and all this is a natural response to the balanced arrangement of charge distributed in each dipole. An immutable imperative, laws of charge, have moved those strings into a symmetrical and balanced arrangement. Those strings close to form circles within circles within circles. Let's assume for the purposes of this argument that this is the nature of a string, and multiple strings form a magnetic field. If so, then what makes that field invisible? Why is it that we can't find particles of any description inside that field? And this question leads us to consider what we can see within our own dimensions of time and space. Here's the thing. For exact measurement, we need light. We use photons in a wide variety of frequencies to reflect the colour, shape, and structure of all material in our visible universe. It's the most accurate gauge that we have. And light travels at the speed of a fraction under 300,000 kilometers per second. This means, for instance, that the photons from our sun would take about 8 minutes to reach us. We also know that light is particulate, and paradoxically that it's also a waveform. And finally, we know that nothing can exceed light speed. However, if anything moved faster than light, then how would light itself find it? If the material moved faster than the photon itself, then it would have come and gone before light could interact with it. At best, the interaction would be partial. Therefore, if the magnetic field does indeed comprise particles, and if those particles are both faster and smaller than light itself, then the field would be invisible. Effectively, therefore, light represents the boundary limit to our measurable dimensions. Anything faster, and it's simply out of reach. What exactly is a boundary constraint? Imagine that we have a machine that propels stones. It operates in a vacuum, so we don't factor in friction, and it throws stones with a constant force. Therefore, the bigger the rock, the shorter the distance thrown, and correspondingly, the smaller the rock, the further the distance thrown. But too big and the machine would be destroyed. Too small and the machine won't notice those rocks. Those extremes represent the boundary constraint. Therefore, what we're proposing is that a particle of light, although being very, very small, is yet much bigger than the particle in the field. It's outside the boundary constraints of the field. The one is entirely invisible to the other. They're out of touch. They cannot interact. The field would simply bend around that particle. And as mentioned, the field itself comprises its material of magnetic dipoles that are organized as would magnets naturally organize. Then they would effectively comprise 3 dimensions, being the first dimension of only length, then many such circles being the second dimension of length and width, and then many more such circles being the third dimension of length, width, and depth. And those 3 dimensions of space share our own dimensions, because we know that they're interactive materials in our visible universe. What does not correspond is their time frame. Essentially, the movement of the field will always precede the movement of light. And the field has no interaction with the particle. It bends around that particle, while the particle is too big to allow for an interaction. We've argued that for anything to interact, there needs to be some correspondence in size to enable that interaction. But what exactly is this difference in size? And can one particle, however minuscule, still be considered bigger or smaller than another? And does that volume of the particle somehow relate to its frequency? Here's the analogy. Imagine, if you would, a father racing his toddler to the other side of a room. This is not your average toddler. He reaches the goal at precisely the same time as his dad. But to get there, the toddler had to take many more steps. His speed, therefore, relatively to his size, was therefore greater. He effectively had to move at a higher velocity relative to his size. Now, back to the photon. We know that photons have an almost infinite variety of frequencies. Let's now assume that those frequencies relate to the volume of each of these particles. Our red photon would be huge, and our ultraviolet photon would be small. For those particles to both move through space in the same time period, then the ultraviolet needs must take considerably more steps than the red. Effectively, both particles would adjust their frequency to conform to light speed. If the one photon is half the volume of the other, then unarguably the smaller would need to travel at twice the speed of the bigger just to keep up. Our most dependable constant in the world of physics is the speed of light. But what we've now argued is that this constant says little about the velocity of the particle. It only describes the distance the photon will travel in a given moment of time.